Now if I am substituting 4 in equation 1, I will get VO upon VI. I am writing equation 1 and 4 again. Equation 1 we had got VO equals to minus GM VGS into RD parallel RL. This was equation 1, and the previous equation final what we had got is VGS equals to minus VI upon 1 plus GM into RSI. So equation 1 and 4. I can substitute this equation 4 in equation 1. So what I can say, substituting 4 in 1, what I will get, VO equals to minus GM into minus VI upon 1 plus GM into RSI multiplied by RD parallel RL. So if this VI goes on the other side, it will be VO by VI, which is nothing but your voltage gain, which will be GM upon 1 plus GM into RSI into RD parallel RL. So this is how we have got the relation for the voltage gain. Now in the problem they have told us to find the output voltage VO. First let's complete the derivation for current gain, then we can go for the final output voltage. Now what you can predict from this voltage gain equation, your voltage gain AV is positive, which implies output and input are in phase. If the sign is negative, it indicates that both are out of phase, right? If I am considering that input is the current source, we need to find the current gain, which is nothing but AI, which is IO upon II, that is output current upon input current. You can say when I am applying current division rule, my IO will be current flowing through RL. So the opposite resistance will come in the numerator, that is RD upon RD plus RL into the total current. Now current flowing is GM into VGS, but the direction is this, so it will be minus GM into VGS. How come? Suppose say you have, what is current division rule? You have two resistance R1, R2, and this is the direction of total current. If you want to find the current through R2, which is say I2, so I can write I2 as R1 upon R1 plus R2 into IT. This is when the current is flowing towards the junction. Here the current is flowing away from the junction, hence you have a negative sign in the equation, calling this as equation number 5. Now if I am applying KCL at A, this we have got by current division rule. Now KCL at A can give me current flowing towards A is II plus GM into VGS plus this voltage drop, you have VGS upon RSI, that is current flowing through this resistance RSI, which equals to 0. So if I am taking VGS common, it will be GM plus 1 upon RSI equals to minus II, which can be further written as VGS 1 plus GM into RSI upon RSI equals to minus II. Therefore VGS can be written as minus II upon 1 plus GM RSI multiplied by RSI, calling this as equation 6. Why we have got? See, for current gain we required IO upon II. So if I am getting this VGS in terms of II, my problem is solved. Now what I will do, I will substitute 6 in equation number 5. So what we will get, IO equals to RD upon RD plus RL into minus GM. This is fixed, and instead of the VGS I am writing minus II into RSI upon 1 plus GM into RSI, right? When this negative goes, it becomes positive, and I can write IO upon II, which is nothing but my current gain AI will be RD upon RD plus RL GM into RSI upon 1 plus GM into RSI. Now if my GM into RSI is very much greater than 1, so what will happen? GM into RSI upon 1 plus GM into RSI will be equal to GM into RSI upon GM into RSI. So this will be cancelled and you are left with 1. And if say RD is very much greater than RL, So my current gain will be 1 in this case, because RD upon RD plus RL will be approximately equal to 1. Why? This value is very much less as compared to RD, so we can neglect this. So RD will get cancelled and this bracket will be 1 and this is 1. So 1 multiplied by 1, the gain will be 1 in this case, or you can say unity gain, right?